Hello everyone and welcome to CCNA Scaling Networks version 6, looking at chapter 4, Etherchannel, hot standby routing protocol, and a little bit of stacking at the end. Link aggregation, Etherchannel. We're looking at now, we've got connections between multiple switches, and instead of just paying lots of money to increase the bandwidth between your connections, we can now do it for free. We just grab a couple of ports at each end and we go from a gigabit uplink to a 2 or a 3 or 4, anywhere up to 8 gigabit connection between two switches for free, because you've already paid money for the ports. So you just bundle up multiple physical interfaces into a single logical connection. So Etherchannel interfaces are done, creates a virtual interface and all your commands are done on that. No need to upgrade the physicality. It load balances. It does a load balancing across the channel itself. As far as spanning trees, we just looked at spanning trees. Spanning trees concerned, it's a single interface, and there's redundancy. Let's say you got 2 or 3 physical connections in an Etherchannel bundle, and if one of those fails, the other 2 just pick up the slack like nothing happened. So it's actually pretty good for redundancy as well. There are a few caveats and restrictions. For example, the maximum amount of physical interfaces per logical bundle or group is 8, and some of the smaller switches, so it's going to the material and your chapter exams, only support 6 Etherchannels, because where most of the CCNA looks at the 2960 series of switches. However, if you do go on to bigger 37s and 38 series switches, they do support more, but for the sake of your exam, there's 8 ports per channel and maximum of 6 channels per switch. So, like all good standards, there are 2 of them. We have, the first one is Port Aggregation Protocol. This is Cisco proprietary, and it has a series of keywords to enable it. So if you say channel mode on at both ends, it's just on. It's hard on and there's no negotiation. If one end is desirable and the other end is desirable, it'll come up. If one end is desirable and the other end is automatic, it will come up. If one end, all other combinations, it won't work. So you've got 3 keywords for port aggregation protocol, is either on, desirable, or auto. So for example, if both ends are auto, it will not negotiate into an Etherchannel bundle. Link aggregation control protocol is the open standard. So if you've got a Cisco device and a non-Cisco device, or a VM server, or some sort of Linux box, or adapter teaming on a Windows box, you'd want to use LACP instead of PAGP. So on is on, same as before, but instead of auto and desirable, now we have active and passive. So active on, active passive on, but if you have passive and passive, then you won't get, the bundle won't form. And if you have on in any other state, it won't form as well, because just like in PAGP with desirable and auto, active with passive, they'll only ever listening. So with auto in PAGP, it's only ever listening. It's a bit messy, but I'm hoping that it might sort of, give a bit of a clue. So PAGP is auto and desirable. LACP is passive and active. So you can see that passive and active, or active and active, yes, or auto and desirable, or desirable and desirable, yes, and on, yes, and all other combinations are not going to form a normal Etherchannel bundle. Speed and duplex must match. This is very, very important, because the devices use CDP neighbors to talk to each other, and if one end is half duplex and the other end is full duplex, or the VLANs are on the wrong VLAN, or the native VLAN is mismatching, these are all the things that are going to stop an Etherchannel forming. So you always need to make sure that both switches, both the interfaces that you're grouping together, are identical at both ends. So, how do we do it? Well, interface range, fast Ethernet 0/1 to 2. Channel group is the command that actually creates the channel. The number 1 represents the virtual interface that we're creating, and then the mode. So we've got 5 choices. We've got on, we've got active or passive, and we've got desirable and auto. So this example we're doing LACP, so we're using active. And now notice the very second that you press enter on channel group mode active, it creates a virtual interface. It says I've just created port channel interface number 1. And then you change to that interface, and then you put your commands. So if you put in 5 commands in the virtual interface port channel 1, those 5 commands will automatically appear on fast Ethernet 1 and fast Ethernet 2. Now this is the way it's meant to work. Unfortunately, in the real world, sometimes it's a good idea to set up fast Ethernet 1 and 2 with every command you need and make the very last command channel group 1 mode active, because sometimes the commands don't bleed from the physical interface to the virtual, and vice versa. Sometimes if you go into that interface after you've made the channel, it'll actually give you a warning and say, stop, you've made me into a port channel. If you want to make any changes, you should go interface port channel 1 and then make those changes. So in the labs, you should follow it this way, but just note in the real world, sometimes you need to just double check that if you've made a change in the physical, it's represented in the virtual, and if you made a change in the virtual, it's represented in the physical as well. Show commands, show interface port channel, show Etherchannel summary. Etherchannel summary is probably the command you'll be using the most because it gives you a nice little summary. See down the bottom here, we've got port channel 1. It is currently S and U, so therefore it is a layer 2 connection and it is in use. The protocol is LACP, and ports FA0/1 and FA0/2 are currently actively in use, bundled in that channel. So show Etherchannel summary, very useful command for verifying your Etherchannel. So once again, problems. On the left hand side we've got channel group mode 1 on, and on the right hand side we've got channel group 1 mode desirable. Now, as we talked about before, channel group mode 1 desirable and channel group mode 1 on shouldn't work, and it won't work. So you need to think to yourself, well, which one do I need to change? Now, years ago, I was a big fan of channel group mode 1 on. So I'd force all of my interfaces to be on, but then you've got a little bit of a risk of spanning tree. Because if you plug it in and the switch 2 is just blank, that will actually make a loop, because it'll be 2 ports on 2 and 1 port on 1 and cause a loop. So I'm sort of leaning towards saying that switch 2 is actually correct. So channel group mode 1 desirable is actually better, because if the channel doesn't form, then spanning tree will just treat interface 1 and 2 as separate interfaces and you won't get a loop. But then when the channel comes up, then they'll logically bound into a single interface, and then spanning tree again will be happy. So different schools of thought, but I'm pretty sure that channel group 1 mode desirable is probably a better way of fixing this problem. A safer way. Now, we've got this lovely redundancy. We've got our core distribution and access model and everything's running fine, and oh no, we've got an interface problem on R1. So we've got R2 sitting there, but PC1 says, oh no, I can't reach my default gateway anymore. It's cut off from the network, even though there's all this lovely, beautiful redundancy in the back end. PC number 1 can't actually utilize it or get to it. So we need to offer our clients a first hop redundancy. So let's have a look at how we get that achieved. We have the router on the left and the router on the right. The router, they can both touch the internet and they can both gain access to the LAN. But what they're doing is they're talking to each other and they're creating a virtual gateway. And that grey router in the middle, that doesn't exist. That's a virtual IP address, and that's what we tell all of our clients to use for the default gateway. This way, if for any reason the router on the left dies or fails, the router on the right will take over the responsibility of servicing that 192.0.2.100. So the clients don't even know. They don't even know anything has changed at all. And that's really, really useful. So we're providing a virtual default gateway so that we've got a couple of routers working together for redundancy, our first hop redundancy. HSRP is the one we'll spend the most time on, basically because that's Cisco's proprietary first hop redundancy protocol, but it's also got a lot of extra features that the other two don't have. So we'll look at what they all do, but we'll spend most of the time focusing on HSRP. Now, HSRP's got a really interesting feature which some of them don't have, is that not only do they present with a virtual IP address, they present with a virtual MAC address as well. So this way, when the main router dies and you fail over to the backup router or the standby router, the clients don't even need to re-ARP or anything because it's the same virtual MAC address as well. And HSRP identifies itself with a vendor code for virtual MAC address. So whenever you're looking at a MAC address table and you see 00000C07AC, that's HSRP. That's fixed. And there's a group number. What is the group all about? We'll talk about that in a minute. But in this example, that's group number 1 because the last 2 characters are 01. The forwarding router and the standby router, or the active router and the standby router, talk to each other with little multicasts every 3 seconds. So that's how they keep track of each other. So if you're setting up an access list or a policy control, you better make sure that UDP 1985 is allowed between them. So if they miss 3 hellos, then the standby router assumes that the currently active router is dead and will take over the responsibility. And because the MAC address changes, the clients don't need to learn a new MAC address. So these are the commands. We have got the left-hand router and the right-hand router, and these are the commands we've got to going. So let's go through and break these down one at a time. First of all, we've got IP address 172.16.10.5, and on the right we've got 172.16.10.6. So they're the real addresses. And have a look at the standby command. Standby 10, IP address 172.16.10.1 is identical for both. That's the virtual IP address that they're going to be using. Now, priority. When you get the opportunity to choose which one is going to be active and which one's going to be standby. So the default is 100. So as soon as you set the priority above 100, then that router is always going to be the currently active router. So as you see with the right hand router, I've set the priority to 90. So that one's always going to wake up, and by default it's going to be the stand up. The word preempt is really, really important. I have no idea why it's not default, but it's there. So what happens when left hand router dies and the right hand router takes control? When the left hand router comes back without that word preempt, then the right hand router would just stay forwarding, even though it's got a priority of 90 and the left hand router has got a priority of 120. So the word preempt means that every single time a router wakes up and says, hello, I'm here, with HSRP, there's an election. And they say, right, actually, you know what? I am the boss and I'll stay the boss, or I am the boss, oh no, there's someone with a higher priority than me, so I'm going to now let them become the boss in my place. Preempt. Now the track, we don't talk much about tracking, but it's a very, very useful tool to use things. So for example, in this example, we're tracking serial 0. So if our serial interface goes down, then we're not going to be able to see the internet anymore. So there's no point for me to be the default gateway. So what I'm going to do is, if my internet goes down, my serial interface goes down, I'm going to decrement my priority by 40. Therefore, my priority is now 80. So the next 3 hellos, the right hand router is going to say, well, actually, I'm better than you now. So he's going to announce himself as the new active router, and the left router will become the standby. Then once that serial interface eventually returns, then we're going to have the priority jump back to 120 because the preempt exists. Therefore, there'll be a new election, and then the left-hand router will take on responsibility again. You can track lots of things. You can track routes. You can track SLAs. Tracking is a really useful tool, but it's not really covered. But we can talk about it later. The group number. The group number is really important. What that means is you can have multiple standby. You can have 4 routers, and you can have 2 default gateways, and you'd have group 10 and group 11 or something like that. The other reason why the group number is important as well is because it gives you a unique MAC address, and I'm a big fan of unique MAC addresses because some older Cisco switches don't like the same MAC address appearing on 2 different VLANs, because HSRP is the same MAC address. So you don't want a router with 5 VLANs on it all using the same MAC address. So it's better. It's just a best practice. VLAN 10, group 10, VLAN 20, group 20, VLAN 50, group 50. The only drawback is your group numbers have to stop at 255. So if you've got VLAN 500, then you might have to be a bit more creative with your group numbers. Show standby. Super duper useful command. So let's break down the comparison between the show standby command and the actual commands that were programmed. So 3 seconds, 10 seconds, default hold down timers. Standby 10 priority 95 preempt. That's the command we typed. So the group number 10. Remember, it's a hexadecimal MAC address. That's why it's 0A in the MAC address. 95 is the priority. Preempt means may preempt. So standby 10 IP address and the IP address you want. Once again, the group number. That's the actual hot standby IP address. That's the IP address. Currently, this router is in standby. It says the local state is standby and the standby router is local. And you can see just above that line, the active router is 172.16.10.5. So that's the actual real IP address of the currently active router. And it expires in 9 seconds. Once again, if no priority is set, then whoever speaks first will become active. But if there's no priority but there's preempt set, then the person with the highest real address will become active. And I've sort of already talked about why we need a group number. I like the group numbers because I like the MAC address to be unique, so that there's no way that a switch on the fringe of your network can see the same MAC address on 2 different VLANs and get confused. Now, there are 2 other standards we're going to look at. So HSRP is a Cisco proprietary. We also have VRRP, or Virtual Router Redundancy Protocol, and GLBP, Gateway Load Balancing Protocol. So Gateway Load Balancing Protocol is also Cisco proprietary, but it has a few caveats and a few little idiosyncrasies that are different to HSRP. So rather than an active and a passive, it has a forwarding and a standby, but they're both working. So they just do a round robin. So every second ARP request that comes along will be given to the user. So when PC1 does an ARP, it may go to the left-hand router. PC2 does an ARP, it may go to the right-hand router. PC3 does an ARP, it may go to the left-hand router. So that means, what that means is that the MAC addresses are still real. So they've got a virtual IP address, but physical MAC addresses. So when the forwarding router fails, we have to rely on the ARP cache timeout and the client to be broken and then do a fresh ARP and get the new MAC address for the virtual IP address of 192.168.2.100. So because the MAC address is tied, the users may notice a bit of a downtime. However, all the routers are forwarding, so you've got double the amount of bandwidth. So, swings and roundabouts on GLBP. So HSRP, a lot of text. Sorry about slide with too much text. So the active router is the default gateway. If the active router fails, the standby takes over. HSRP has versions, but you don't really need to know about that. But the best thing about version 2, I guess, is you can have a higher number than 255. HSRP uses different multicast addresses and supports IPv6. You can also have authentication, but we don't really worry about that. Election process, you've got to have that priority command and you've got to have that preemption. That's what gives you the ultimate control. You don't want to leave everything set on automatic. Initial, and so when HSRP initializes, then it begins to learn, then it listens to what multicast it receives, then it goes to standby. If there's already an active, it'll stay in standby. If there isn't, and if it's alone, it'll go to active. Now, if you got two routers, one standby, one active, when the third one comes along, it will just stay in speak. So yes, you can have 3, 4, 5 routers in an HSRP group if you wanted. Now, Stackwise. We talked a little bit about Stackwise in the previous module, but now we're going to talk a little bit about more. Sorry, previous chapter. So, Stackwise. 3750s, 3850s, 3950s. They have this lovely, and some of the 2960s, and even the 9000 series, 9200s, 9300s, they have these lovely stacking cables on the back. The data stacking cables allow you to bond a group of switches into a single entity, a single management device. So it just appears to be one switch with lots and lots of ports. The other good thing about Stackwise too is that there's also Stackwise for power. So you have power redundancy for the Stackwise on the back. So that if a power supply fails, then the extra load, extra capacity in the power supplies will just pick up the load of the missing power supply in the middle of the stack. The only caveat is at the moment, it may change because I haven't checked the 9000 series, but with the 3000 series, you can have 9 switches in a stack, but you can only have 4 in a power stack. So you've got to be a bit sort of creative with your power redundancy. So this is a bit more of a diagrammatical form. So we've got 2 switches on the left. So instead of having 2 just isolated switches with a link between them, we've bonded those into a single switch. So ASW1 and ASW2, they present themselves as a single switch. So those 2 ether channels coming from the distribution layer switches, they're not going to have any trouble with spanning tree or anything like that, because as far as they're concerned, there's one switch at the other end and it's got 2 links to it. Now, my facts and figures, 16 gig and 32 gig. I'm pretty sure the new model of Stackwise is much faster than that. And Stackwise cables, the speed comes with a sacrifice. So 50 centimeters, 1 meter, and 3 meters. You cannot do physical stacking across multiple buildings. That just doesn't work. They have to be in the same rack pretty much. So, when you want to build a stack, you need one switch to take charge. So you need to say, all right, your switch number 1, you are going to be priority of 15. So now we need to tell switch 1, there's going to be a switch 3 and there's going to be a switch 4. Now this is a good thing about the Stackwise actually, they don't have to be identical families. You can mix and match PoE, you can mix and match some of the characteristics. It's not advised, but it can be done. So once we've provisioned this up, even though we've only got one switch on our bench, if we do a show run, it'll show us, what have we got there, 72 ports. Even though we've only got one physical switch, when you do a show run, we're going to see gigabit 1 to 24, gigabit 2/1 to 24, and gigabit 3/1 to 24, sorry. Now, so all we need to do is get out the second switch and say, all right, new switch, you are now switch number 2, and your priority is now 12. And then we get out switch 3, and we say you are switch 3, and you are priority 10. And then you turn them off because you got to reboot them for them to be A, renumbered, and B, get their new priority. Oh no, just to be renumbered, you got to reboot them, and they'll just sit there saying I'm switch 2 and I'm switch 3 completely blank. All you got to do is plug the Stackwise cables in the back and they'll automatically bond into the group, and they will just be part of the stack. So you could spend 3 hours programming switch 1 and making it perfect, and then you only need to spend 5 minutes on switch 2 and 3, and you just plug them in and they just get the whole config. That's the other good thing about the stack, is that all switches have a full copy of the running config. So if the master dies, you don't lose anything. You could lose 2 or 3 masters and then just replace them with blank switches, and they'll get their config from the other switches. But if you plug your console cable in the back, they will warn you and say, actually, you know what, I'm not the master, you should plug into the master. So just bear that in mind when you're consoling into them. But if you use SSH or Telnet or PuTTY, they will just logically be a single unit. You won't see 3 switches, you'll just see 1 switch. So, just for fun, show switch detail. So you can see that we've got switch 1's got a little asterisk because he's the master, and he's priority 14, switch 2 is priority 12, switch 3 is priority 10, and everyone's ready. And the second thing is the ports on the back. So all 6 ports are okay, and you can see how the port 1 on switch 1 goes to 2, and so it's a daisy chain, it's a loop. And then shows ring, because we've done a full loop, and these are only 3750s, we've got 32 gig worth of backplane in the back. The newer 38s and the 9000 series are faster. Stack power, I've already talked about it, but stack power is a really useful thing. So the photo on the left represents the 38 series, where the stacking data cables are slightly different, but the stack power cables are still the same. So they share power. It's really awesome. The other good thing you can do is you can get like 4 switches with like mediocre power supplies, and then just get an extra power supply. Because it's a bit hard to see with the photo, but they have 2 power supply slots. So therefore you just put in when you buy 4 switches, you buy 5 power supplies. And then you know that if one power supply fails or someone pulls the power cord out, those stack power cables are going to provide fully redundant power throughout all the switches in the stack. So even if the power supplies are at their limit, because you've bought a spare one, then that one's going to take over and there'll be no outage. They'll send you messages and alerts, so you just walk over there, figure out the problem, but there's no outage. That's why stack power is so great. So once again, show the stack power. We can see that there's one power plan, and it's got 1750 watts capacity, and it's only allocated 760. So there's a lot of headroom there. And like I say, I haven't actually tested this. I haven't actually gone out there and done a lot of time ripping out the power cables, but based on the math alone, I could pull out like a couple of power cables, and these 4 switches wouldn't even miss a beat. They would be completely happy just to go on, keeping on working, no problem whatsoever. So stack power, very, very useful piece of redundancy on your network. Stackwise cables are awesome, but they have a physical limitation, and that's the physical distance it takes to run that 50 centimeter, 1 meter, or 3 meter cable. So what Cisco have done is said, you know what? We also offer you the traditional old school stacking, and that's a virtual stack. And there's no distance limitation because they use the interface on the front. So whatever the limitation is of the interface on the front, that's your limitation. Could be a gigabit connection on copper, could be a gigabit connection on fiber, could be a 10 gigabit connection on fiber, which could go 5 kilometers, 10 kilometers. So that physical distance limitation is now gone, but it's philosophically the same. So instead of having a physical stack that has to be right next to each other, this is a virtual stack, just using standard Ethernet style connections. So now, for our standard setup, we have a switch on the right hand side, 2 switches that are now stacked but using normal Ethernet interfaces. So we go into switch 1 and we say, let's create a domain, so it's like identifying it. We say your switch 1, and then we go do exactly the same command on switch 2, and we say your switch 2, and then we find the interfaces that the two are talking to each other on, and then we say switch virtual link 1. Done. Now those two switches, so those interfaces won't be used for normal Ethernet anymore. They are now proprietary special connections between those two switches, making a virtual switch link. So exactly the same as Stackwise on the back, but now using cables on the front. But when you do a show run now, you won't see two switches anymore. You'll see one switch. Now, like I said, I haven't done this in a lab environment, and there are no labs to do this because we don't have the equipment. But there's plenty of different case studies about setting up virtual switching systems. Thank you very much. See you on the next one.